This data in MyOpenMath is REG data. And this is from India. There's a lot of data sets from India. And India has a rainy season in March. So this is the drainage in meters squared per second over watersheds in India. And it has the drained square meters, the temperature at the basin, the general basin, the average temperature, the PPT is the precipitation, it's the rainfall. Average temperature of the area, the average temperature at the site of the gauges, the relative humidity of the basin, the March precipitation, and this is the median steepness. And steepness is measured by area versus the length of the watershed. So that if it's steep, it's got a small area for the length of the river. And we're going to predict the maximum. This is the 90% maximum. They don't throw in the floods, that sort of thing. So we need the data analysis tool pack, because we need to run a multiple regression, or at least do regression the easy way at the least. And we're going to run regression on it. The input range is the max drainage, or the max meters squared per second. And there's 200 observations, 300. That's the independent variable. The X range for the dependent variables is everything else. And we're going to keep the column titles. We've got labels in the first row of each one. The output range, doesn't matter where it goes. And we want residual plots. And this is going to show us the residuals, the mistakes in the predictions by each one of the variables. So this is the layout of the results. The R square is 0.29, which is pretty low. And we wouldn't expect the same thing as fish length and weight, but it still should be better than 0.29. Down here in the T statistics and the coefficients, the only thing that is significant is the drainage in square kilometers. Everything else, including the intercept, is nothing. One thing with the intercept is that it could be zero. If you look at the 95% confidence interval and the P level, the 95% confidence interval includes zero. So it could be zero. But it's got to make sense if we're going to make it zero. Does it make sense that if there is no drainage, there's no water, which this would imply? So if we made this zero, we have a reason for it. But you can't force a regression through zero unless you've got a really good reason. And this one is almost significant, and it's not doing anything anyway. It's not hurting anything in particular. But we would expect more to come out of this. In particular, the March precipitation, the rainy season, is not significant. So that this, at what we've got, basically says the drainage area is all that matters. Something's not right. We don't know what's not right, but something's not right. The thing to look at is what is significant, and it's the drainage in square kilometers. And if you look at the drainage areas, this is square kilometers. This drainage is 2,253 square kilometers. 1 square kilometer is like 247 acres. This is 250 times 2,253 acres. This is big. But if you look down, here's one with 53 square kilometers. There's another one in here that's less than that, 203, a 30. There's a 20. Okay, the range is huge, and we want to know what the deal is. We're going to make a box plot to look at the possible outliers. To do that, mark the square kilometers of drainage. Don't get the title in it, but we need to do this to get the box plot. I'm going to insert a recommended chart. So go to recommended charts and all charts, and we want to make a box and whisker plot for this drainage. And this is it. Most of these things are below 5,000, half of 5,000. This one in particular is immense. And in this box plot, every one of the dots here above this line, this is the third quartile. Every observation is 1.5 times the interquartile range that's outside of the third quartile. Basically, there's all this information in here, and then there's some really big drainages. To look at it more, we're going to copy this column and put it on another page just to get it out of the way, so when we do something, we don't screw up what we got. Always make a copy of the original before you do anything even slightly different. So I went home and copy. And I'm just going to the next page. I'm going to insert a page and paste that column in there. Normally you'd have to look at the sizes of these things to get a frequency distribution possibility. Basically, these are, from looking at the box and whiskers plot, we want 10,000, 20,000, 30,000. And I'm going to just use the fill command and make this go down to 90,000 in steps of 10,000. And there's nothing in there bigger than 90,000. This is going to be a frequency distribution. This is like we did on one of the first days. Okay, so I'm going to make a frequency distribution out of that drainage data. Something's not right. Equals FREQ. Frequency comes up. And the data array is all of the drainage area, and the bins array is the 10, 20, and so forth that we got here. So that's a frequency distribution that shows basically the same thing as the box and whiskers plot, except it's a little more obvious. But of these drainages, And I should have done it by 500s or 5,000s because 289 of these things are less than 10,000, and the others are much, much bigger. So if I do this by 5,000s instead of 10,000s, I want to know what the spread of these things is. So I'm going to do another frequency distribution. When you do these things, you never get to do just a regression or just one thing. There's always something that you need to look at before you get carried away making statements. So here I've got a 5,000s, and I'm going to do the same thing. Mark that area, equals frequency, mark the data, comma, then the bins array, which we just put in, and now 284 are less than 5,000. So that 284, there's 293 altogether. 284 divided by 293 is 97%. 97% of the data is less than 5,000. 9 of them are huge compared to those. We've been dealing with things up in the 30,000 square kilometers. So we're going to take out everything bigger than, well, we may as well do it at the 1,000 level, 10,000 level. Everything bigger than 10,000 we're going to remove from the analysis and see whether that affects what we got. Go back to the original data, and I'm going to copy all of this data. And if you're ever at the top of a long list, mark something across the area you want. Do Shift, End, and down arrow. And it takes all of it and marks it. So you don't have to scroll through things. Sometimes you get 100,000 observations. I'm going to copy all of that, make a new page, and paste all that original data. Because I'm going to screw with this, and I don't want it to contaminate the original data. We want to mark all of it again, and we're going to sort. And I've got the column headings highlighted as well. The Home tab over here on the top right is Sort and Filter. Click on Sort and Filter, and if you just have a single column, you can do smallest to largest, largest to smallest automatically. We want a custom sort because we want to sort on the drainage area. And it shows everything we got, and up here at the top it says my data has headers, which it does, because if this isn't checked, it tries to include those letters in its data, and it won't do it. And we can sort by, and because we have the headers, we can sort by the variable name. So here's the drain, square kilometers. We want to sort it smallest to largest, and we're sorting on cell values. You can do all kinds of strange sorts. Nothing else changes except the order of the drain, but all of the columns change with it. So we've got the right drainage area and the right precipitation, temperature, and so forth. So we're going down. We want to go down in drainage, and we're going to take out everything bigger than 5,000 basically, because that's what we had in our sheet. So anything bigger than 5,000, we're going to be down to 284 observations. So here's 400, 600, 1,000. These last 9 are bigger than 5,000. And we got 4862, and it goes up to 25791, 25,079. Just erase everything that's 5,000 and above. 5,000 is the cutoff, 4999. So I've taken out a bunch of observations. And I have to have a reason to do that. And basically my reason is something's not right and I want to see what it is. And drainage is the only thing that's affected it so far. Then data analysis, regression, and it doesn't change the original selections. So you have to start over for those, basically. The Y range is the meters squared per second, or cubic meters per second. All of that is selected. The X range is everything else. Everything that is not that drainage area, I want in the analysis. And I should have 284 observations when I get done. Okay, and here is my new result. The R square is worse, and still the only thing that is significant is what? Nothing. It's the big drainages that drive the regression. We actually took out what makes the regression work. So that if we were going to do this for real, we would go back and take out the small ones. We have to find out what people think is a significant area for the drainage. Have to look at where it is and what is dependent on that. Is somebody trying to prevent floods? Is somebody trying to keep water? This is how they decide where to put dams. You don't put a dam across the smallest drainage, you put it across the big one. And the Colorado River, for example, the drainage for that is huge. We have no concept of it. In fact, we have, in Blacksburg, we have the Eastern Continental Divide. And if you go up on one of the streets in Blacksburg, just at a house up there, anything that drops on the right side of the road goes to the Atlantic Ocean. Anything that drops on the left side of the road goes to the Gulf of Mexico. So we have our own huge drainage, and the New River is part of that, except the New River goes the wrong way. It goes north. It's one of the few rivers that do. So drainage is a complicated deal. But basically, we just gutted the thing. And we need to go back and look at it again. All of statistics is after everything you tried to do and everything you figured out what's going on, so that you aren't analyzing something that means nothing. I'm going to go back and take out some of the other stuff, because at one time I got an R square of 0.537. I used drainages less than 40,000 instead of 50,000. I need to remove more of them. Something's going on in there, and I don't know what it is. Okay, so that's all we're going to do with that one. Go back to My Open Math, and this is advertising cost and sales. This is revenue from advertising on TV, radio, and newspaper. and this is the sales total for these organizations. We want to find out what to put our money in. Where should we buy advertising? Somebody is tracking those things to see what is effective. We're going to do a regression on this thing, but first we're going to look at the relation between sales and each one of these variables. So we're not doing this blind. We're going to make a graph, a scatter plot of sales on the y-axis and TV on the x-axis. Select data, add x values first. I'm going to use the TV as the x. Shift end arrow down marks it. Then I'm going to use sales as the y, and I can just go back up and mark it. And this supposedly is TV by sales. Is there any pattern in that? Did you get that shape? Yeah, it's supposed to be more of a fan shape. I got something wrong here and I don't know what it is. TV, sales, yeah, it's definitely not supposed to look like that. There it is. I had something wrong. This is a fan shape, and not only that, it's got a curve in it. I want to do the same thing for radio and newspaper sales. Insert, charts. Right click, select data, add, and this is going to be radio. This is radio. This is going to be sales. That's radio. And it looks the same way. What reason can there be for this? We've got a fan shape and a curve. We have some little ones and a lot of big ones with a lot more spread. Where do you buy groceries? You go to Kroger, Food Lion. If you're from somewhere else, there's other grocery stores. There used to be Piggly Wiggly and Wade's. They were much smaller. Wade's was local, and they wouldn't have much money to advertise. So the small stores are down here. The large stores are up here, and they have much more in sales, and it's a wider spread. Down here, in the low ones, it just can't go very far. The same is true for the radio ads. Newspaper is next. Right-click in there, select data, add. X values now is newspaper, and the Y values are sales. Does newspaper look like it's got anything to do with sales? Not a bit. So we're going to do this regression. We expect TV and radio to be important. Why isn't newspaper important? People don't get newspapers like they used to. Most advertising is on TV and online, on YouTube and things like that. Newspapers just aren't doing anything anymore. But also, we've got to do something about this. What was the transformation of the y variable that makes it more of a straight line, that fixes or tries to fix flare? We're going to look at the natural log of sales. Basically, we want to squash this thing, which is all that does. This is ln of sales. And there is no justification for this except we want it to be flatter. Equals ln. And the log base doesn't matter. And then we're going to do another graph of TV advertising by sales. And I'm still in the data, so it tries to fix it for me. Right click, select data, add, and we want TV expenditures by ln of sales. Look at the graph. This is ln of sales. Did I improve anything? Here's the TV graph. Did anything change? All I did was squeeze it. Look at the range of Y values for sales. It goes from 0 to 30. If I go over here and right-click on the axis values, I get Format Axis. I have a minimum of 0, but I'm going to put this on the same scale as the other one. So I'm going to go 0 to 30. What does it look like compared to the original now? So when we squeezed it down, we didn't change the shape, actually. It's the same shape. It's just smashed. But it really is smashed. And now it's pretty straight. So it did what we wanted it to do. The change in log was effective. And we're going to proceed with the log of sales as the Y value. So again, data analysis, regression, and it's still got the old stuff in there from the last one we did. So now the input range is the sales logarithm, and we want to include the title of the column, and the X values is the TV, radio, and newspaper ads. We don't need sales, we just need TV, radio, and newspaper. and I'm going to get residual plots like I did with the last one. I'm going to keep residual plots. I want to look at how the mistakes are distributed. And here's the information on the coefficients and how important they are. The intercept is 50, and it is very significant. That means basically we have a store. Whether we're advertising or not, people are coming to the store. So that's kind of a base for what you could expect to sell. The coefficient for TV is 23.7, and it is highly significant. For radio, 12 something, and it is significant. And for newspaper, it's nothing. There is no association with newspaper, which is what we saw in the graph. But all of these are important, and to use this, 80% of sales is associated with TV and radio ads. Now, this might be different in different areas because TV channels are different. All of this stuff has to be taken in the context of what's going on. We got statistics, but you have to understand what you're dealing with and why it's important and what are you going to do with it. And that transformation that we made for the log of sales has to be accounted for now, because if we put in a TV and radio expense and calculate the log of sales, we have to take E to that number to get the actual sales. So everything we have fit here applies to the log of sales, not to sales itself. Those are the kinds of things that we get. We should do box plots on all of these variables to see whether we're getting skewed observations. We should look at the frequency distribution. We should look at the correlation coefficients between the log and the sales directly, and all the rest of those things. So everything you do up till this point involves everything we did up to this point. All the frequency distribution, the box plots, the average, the quartiles are all in here.